It's an honor and also quite a pleasure to spend the whole year here. So thanks again. The lecture series is Proofs, Approximation, and Expansion. And let me tell you what I plan to talk about in the next today and also tomorrow and Wednesday. So today we will talk about the proofs part, probabilistically checkable proofs. And these are organically connected to approximation. We'll talk about approximation as well. And the connection to expansion maybe seemed a bit anecdotal, but to me, I think it's a deeper connection. We'll talk about that a little today and much more tomorrow. Tomorrow, the main topic will be these high-dimensional expanders. So these are a newer topic of study, a lot of activity in the past few years. I'll talk about definitions, what these really are, and some really nice local-to-global theorems that you can prove on them. And these local-to-global theorems have a lot of flavor that resembles what the PCP theorem says, so there is some connection here. There are these beautiful objects, constructions of high-dimensional expanders that are based on some very deep mathematics. These are arithmetic quotients of infinite Brouat-Titz buildings and things that I understand very little, but the angle that I do understand seems that these are very beautiful objects that have some potential for being connected to PCPs and maybe useful for constructing codes. And I'll try to explain tomorrow kind of my interest in these objects and how they might be useful for this area. So that's tomorrow. And in the third day, I will talk about, going back to approximation, talk about optimal PCPs. So for approximation problems, an approximation problem comes with a number, a real number, which measures how good you're approximating. It's the ratio of approximation. And so a lot of problems that are NP hard to optimize and to decide exactly, you can approximate to within some factors. And now you can ask, where is this number? How does this number affect the complexity? And it turns out that if you assume this unique gains conjecture, we know exactly what the number should be. And there's a very beautiful and clean picture of approximation if the unique gains conjecture is true. And so we will discuss this and talk about some things that we know, recent things, and this will be the topic of the third lecture. Okay, so today I'll talk about just the PCP theorem. So this theorem says that proofs have a format that is very easily checked. You can check it by just tossing some random coins and reading just a few bits. And how did this theorem come about? So in the 1980s, theoretical computer scientists were interested in cryptography, and the rigorous foundations of cryptography were being laid. And then interaction between entities and one person trying to prove to another that something is correct, and all kinds of situations like this were being analyzed and tried to be formulated rigorously. And that's, in cryptography, you must use randomness. You can prove that. You cannot do good encryption without randomness. And that's how randomness kind of came into the picture together with proofs. And this led to the formulation, or at least the thought of this idea of a prover and a verifier that has some randomness. In the end, the PCP theorem is not interactive. There's no interaction in it, but still this randomization is powerful for proofs. So this is where the PCP theorem came from, but very quickly, even before it was proved in its stronger form, it was realized that this is very tightly connected to approximation. So really, the PCP theorem and hardness of approximation are very organically related, and we will see this. Okay, so talk about proofs. Okay. So a proof is very fragile, as we know. There can be a bug somewhere, and it's very hard to find, and you need to really read the entire proof. You cannot just read part of the proof. In fact, if you allow me one bug, I can really prove everything. So to be a bit more formal, what is a proof? So it's a statement that you want to prove. And then the proof is a sequence of statements leading up to the final theorem. And what are the pi i's? They are either axioms that come from some well-known set of axioms, or they follow from the previous pi i's by some well-known set of derivation rules. The derivation rules, of course, need to be valid. What other conditions do the derivation rules need to satisfy? Yeah, I should use the clicker. Okay, that would be better. Yeah, much better. Okay, so it should be easy to check that the next statement follows from the previous statements, right? Otherwise, why do you need the proof? You can just check that T is correct. The whole point of the proof is so the checking is easy. Okay. In fact, if you ask yourself what are the rules for proofs or how to formulate a proof system, really the way to do it is by telling me how you're going to check it. If you tell me how you will check the proof, then I know how to write the proof. So one way to formalize a proof system is to just tell me what the checking procedure is. This is a much more expressive way to formulate a proof system than just axioms and derivation rules, but it's a very good way. This is the theoretical computer science way, anyway. And so for every algorithm that comes with a polynomial time bound, you have implicitly the set of all statements that the algorithm will accept. And these are the theorems that this algorithm checks. Okay, so every algorithm specifies a proof system. Okay? And NP, the class NP that we talk about so much, is just the collection of all such sets. So for every polynomial time algorithm, there is the set of all statements this algorithm accepts. NP is the collection of such sets. And instead of talking about some abstract definitions, I prefer to just give a couple of examples so that it's a bit more concrete. Okay, so here is one example of an NP set. Let's call it solvability. The elements in this set are systems of polynomial equations in variables. So of course, the number of variables can grow to infinity. Suppose we fix some finite field. And then a system of polynomial equations is inside the set if there is a common zero. And it's not in the set if there is no common zero. Okay, so what would be a verification algorithm for being inside the set solvability? Just plug in the values for all of the variables and go equation by equation and check that this point A is a proof for the fact that this system of equations has a common zero. Okay, and of course this verification algorithm that goes equation by equation runs in polynomial time. Okay, here's another example. Three-colorability. It's the set that consists of all graphs that are three-colorable. What's a three-colorable graph? It's a graph like this that you can find a coloring of the vertices so that every edge sees two different colors. Okay, so what is a polynomial time verifier for this language? It's just the algorithm that expects as a proof a coloring of the graph, goes edge by edge, checks that every edge sees two different colors. It's a polynomial time algorithm. So this set is also in NP. So one remark is that both of these examples, the three-colorability and solvability, are two sets that are complete for the class NP. What this means is that you can encode polynomially every other NP set into this set. So it's actually easy to see that you can encode three coloring into solvability, because you can look at the finite field 0, 1, 2, so a three-element finite field, and just write an equation that says that these two values need to be different. It's easy to write an equation in two variables that does that. You write all the equations for all the edges, and you get a reduction from three-colorability to solvability. The other way is also true. It may be less obvious, but it's very easy. You can encode any polynomial system of equations by a graph. And in fact, any NP language can be encoded by a graph. Okay, so here is a picture of some NP sets. So here is one. So you can think of all possible strings as specifying some system of equation, but the NP set here is those that are solvable, the ones that have a common zero. Okay, this is one example. Another one is you can think of strings as specifying graphs, And then the three colorable graphs are a subset of these graphs. Another example. Okay, so you can have all math statements in some well-defined axiomatic proof system. And then the ones that have polynomial length proofs are your NP set. And you will have an algorithm that checks that the proof is valid. Okay, and here's another one. You can have all integers, and then a subset is the integers that are primes. This is a bit different from the other ones, because the other ones are all NP complete, and this one is actually in P. So the fact that all these are NP complete means that you can translate from one to another. So if you, for example, you want to prove some theorem like the Riemann hypothesis, and suppose you believe there is a proof that goes in under 1,000 pages, then you write the appropriate statement in a formal way. You get a statement of length 1,000 pages or so. Sorry, you get a statement and the proof you expect it to be 1,000 pages, and then you can actually translate it to some graph. Maybe the graph will have 10,000 vertices, and the graph is three colorable if and only if this theorem is has a proof. Of course, staring at that graph, I don't know what it will teach us. But anyway, okay, so these are, yes?
I would expect that a 10,000-page proof would transform into a much bigger form.
Actually, probably, yeah, that's absolutely true. But it's polynomial time. No. You don't think so? Why would it be exponential?
At least if you use, for example, the Bourbaki formal system, when you have an exist something, you repeat twice essentially large part of the statement. You take property R of 2x of R, so it's multiplied by 2 the length if you start with just exist x R of x.
I see. I'm not sure. I think you should be able to do everything in polynomial time, but okay, but by adding intermediate values and stuff. But okay, so just to say, what is the P versus NP question here? It's just, is it true that deciding whether a theorem is correct is as easy as checking that the theorem is correct when you're given a proof? Of course, it is not. Okay, one last thing is that sometimes people refer to these NP sets as, in other terms, maybe decision problems or languages. So maybe you've heard that. These are all just sets of
just to answer his question, that is a form of theorem, that some version of theorem proving in that efficient term, ZFC, I think is what we said there. Is that NP complete?
It is NP complete. I think the question was, if you want to translate a theorem in English to a formal statement, I mean, these are all constant size things. What is the blow up? Yeah, but this is a theorem, yes. Yeah. Okay, so let's now look at the NP verifier, this algorithm that checks a proof. The verifier reads an input, like a graph, and then it reads the proof, for example, the coloring of the vertices, and then it does some calculation and it says yes or no. Right? This is the NP verifier. And then there are two important properties. If the input is in the set that we're trying to verify, then there will be a proof that is accepted. That's completeness. And if the input is not in the set, then every proof is rejected. Okay? What is a PCP verifier? PCP verifier is the same thing. It's an algorithm, but now this algorithm has some randomness. Okay, so it reads the input, it tosses some random coins, and then it only reads a constant number of bits in the proof and accepts or rejects. Okay, and now the promise is that if the input is in the set, there will be a proof that is accepted. And if the input is not in the set, then no matter what proof you write down, only a fraction of the calculations will lead to an acceptance. So I think the best way to understand this, because it might be confusing, this relationship between the randomness and the existential quantifier on the proof. So what is the way to think about it? When you look at the PCP verifier and you unravel the randomness, the meaning of having only logarithmic number of random coins is that when you unravel all the possible ways the random coins can fall, there's a polynomial number of options, okay? And for each specific random coins, the verifier is doing something. Maybe the calculation is difficult, but it's only reading a constant number of bits in the proof. So what you have is a polynomial number of calculations, each one of them just reading a constant number of bits in the proof. And what then the soundness says is that, well, actually, let's do both of them. If the input is correct, then there is a proof so that all these calculations say yes. And if the input is not in the set, then no matter what proof is written down, a constant fraction of these calculations will lead to a negative answer. So if you look at these calculations as like steps in your proof, it means that many of the steps will fail. Unlike in a normal proof where one failure can completely ruin the thing, in this proof format, you break it down into many local steps. Each step looks at only a constant number of bits, and yet you know that simultaneously many of them will fail. So this is the meaning of a PCP verifier. Okay, so the PCP theorem was proven, as I alluded to, in the early 90s. And it says that every NP set, in particular all the sets that I wrote there, has a PCP verifier. So maybe I forgot to highlight this, that in NP set, for example, all three callable graphs, there can be more than one verifier algorithm for the same NP set. For example, you can ask for the proof that a graph is three callable by asking for the colors in numbers, or you can ask for the colors in words like red, blue, and green. Okay, formally these are two different algorithms. One needs to read English letters and one needs to read numbers. Okay, so these are two different algorithms. They lead to the same set. And what this theorem is saying is that there is also always another algorithm, a PCP verifier, that accepts the same set, all three callable graphs, but it has this very robust proof format. Okay. So kind of the way to view this is that randomness adds some uncertainty to the proof, because if you're only going to read a constant number of bits, you might make a mistake, but you get more power because you only read a few number of bits. And this is quantifiable. If you're willing to only work with error probability that's very low, like 2 to the minus 1,000, you just need to read roughly 1,000 bits. So this is in fact applicable these days. People use PCPs because an error probability of 2 to the minus 1,000, you can argue that it's smaller than the proofs that we write in English. So anyway, the PCP theorem is actually kind of, at first, the most uses for it were not in kind of proof checking, but more, as I said, in hardness of approximation. Recently, you see a lot of uses of the PCP theorem in proofs of computational lower bounds to prove the average case hardness. I won't go into that. Another kind of area where the PCP theorem gave a lot of interesting definitions and also constructions is in error correcting code. There's a notion of a locally testable code. We will discuss this maybe tomorrow. It's also useful in practice. So this is a development of the last few years. It kind of has been a bit shocking for me to learn this, but people actually use PCP protocols in blockchains and other cloud computing situations where you want to verify some very difficult calculation. The cloud will do the calculation for you, and you on your iPhone will check it. And of course, the iPhone is weak, so you use some kind of PCP protocol to make the calculation much simpler. So anyway. So now, before I want to discuss a little bit about the proof of the theorem, but before I will talk about hardness of approximation, since it is somehow intrinsically connected to the statement of the theorem. Okay, so let me tell you, as a digression, a little bit about approximation algorithms in computer science. So in the 1970s and 80s, people started to discover that many optimization problems that were of interest are actually NP-hard, and we cannot hope to find polynomial time algorithms for them. And then it was kind of natural to say, okay, so we will try to find approximation algorithms. And there were many different algorithms that came about, very beautiful constructions, just showing better and better algorithms, but there was nothing known as a lower bound. There was nothing that said, you know, you cannot do better than anything. And that was the situation. So let me give you a couple of examples so that we know what I'm talking about when I talk about optimization. So here is an example. If you think of polynomial equations, here I can even think of linear equations, and I can even think of linear equations over g of 2. So suppose I have a collection of linear equations, and it's overdetermined, so there is no solution to all of them. I can still ask, you know, can I satisfy as many as possible? What's the maximal number of equations that can be satisfied simultaneously? That's one problem. Another problem is the 3 coloring. So you're given a graph. Maybe there is no 3 coloring. Maybe there is. Anyway, you want to find the 3 coloring that satisfies as many edges. So few as possible edges are improperly colored. Okay, so it turns out that both of these problems are NP-hard, even the one with the linear equations. And so you can think about approximation. So what is approximation? Instead of trying to find the maximal number of linear equations, you are okay to find an assignment that satisfies some alpha fraction of this maximal number. And the same for coloring. Instead of coloring the vertices so that a maximal number of edges are happy, find something that's at least an alpha fraction. And you can expect that the complexity of this problem depends, well, it depends, of course, on that problem and also on alpha. So now, as I said, people discovered many algorithms, and the question is, how would you prove a lower bound? How would you prove that there cannot be any algorithm better than for some alpha? Okay, and here is one way to do it. So how to prove claim? I guess it was supposed to be how to prove and then claim. Here's a claim. Assume that we have an efficient algorithm R that maps any graph G to a graph G prime. And this algorithm has the property that if G was perfectly colorable, so here we denote by opt G, this is the largest number of properly colored edges. So you go over all possible edges, and opt is the maximal fraction. So opt being 1 means that the graph is perfectly colorable. Okay, so suppose our algorithm is such that if opt is 1, then for G prime, opt is still 1. But if opt is less than 1, then for G prime, the gap is much bigger. Then for G prime, every coloring violates at least 1% of the edges. Okay, so in our claim, we're assuming that we have this gap-producing reduction. If we have such a reduction, then max 3 coloring is NP-hard to approximate to within some factor alpha. And it's some factor that's between 0.99 and 1. Okay. Why is this correct? This is very easy. Let me just show the proof. Suppose you did have an algorithm that approximates max 3 coloring to within this factor. What does it mean to approximate? It means the algorithm outputs a value that's within this factor for the correct value. Right? So suppose you had that, then we can have an algorithm for 3 colorability, which is NP-hard. We're not supposed to have such an algorithm. And how do we do that? Well, we get the graph G. We're supposed to decide if it's 3 colorable or not. We feed it to this R that amplifies the gap and produces G prime. And then on G prime, we run this approximation algorithm that we assume exists. The approximation algorithm will tell us if it's roughly here or roughly here, and then we will know if G was a good or a bad instance. So this is how you move from optimization problems, which are like functional problems, to decision problems. It's not very interesting, but the interesting thing is this, this claim, this part of the claim, which I will now, in the next slide, show that this is equivalent to the PCP theorem. So this claim is telling us that if you had proven the first part, it follows that some hardness of approximation result. So in fact, here are 2 equivalent formulations for the PCP theorem. Okay, the first one is the one we discussed before, over here. And it says that every NP set has a PCP verifier. So there is an efficient algorithm that reads the input, it tosses some random coins, and then it reads some constant number of bits from the proof and says yes or no. And it has the property that if the input was 3-colorable, the verifier will accept. And if the input was not 3-colorable, then no matter what proof it sees, it will, there's some 1% chance that it will reject. This was the proof formulation. And this is equivalent to the approximation formulation. And here the statement is what we had in the previous slide. There is some efficient gap-producing reduction R that takes any graph G to a new graph G prime. And the property is that if G was 3-colorable, still G prime is 3-colorable. But if G is not 3-colorable, then G prime, any coloring will violate 1% of the edges. Now, what is the connection between these two things? So at least showing, oops, what happened? Sorry. Yeah. Yeah, okay, sorry. At least showing this direction is very easy. Suppose I know this theorem and I want to have a verifier for 3-coloring. What I would do is, if you tell me, if you give me a graph G and I need to get a proof for its 3-colorability, I won't ask for a coloring for G, because that won't be good. I will, in my head, convert G to G prime using this algorithm and request as a proof the coloring for G prime. And the coloring for G prime I can check by just taking a random edge in G prime and testing it, because I know that if G was not 3-colorable, G prime would have many violations, and I will catch this violation. So this is supposed to indicate the connection. Actually, the connection is very easy in both ways. And interestingly, this connection was made even before the theorem was completely proven. And this hardness of approximation and the PCP kind of grew together. Anyway. Now, the interesting thing that I want to point out is that this approximation ratio, alpha, which was 0.995 in my previous slide, is some number that gives you a smooth interpolation between easy and hard instances, even of 3-coloring, or for every problem. On one hand, when alpha is very close to 0, the problem becomes easy usually. On the other hand, when alpha is close to 1, the problem can be very hard. So it was very intriguing for people to understand how this smooth parameter interpolates between the complexities of the problem. Okay, and for example, for linear equations, we have this theorem, a beautiful theorem of Hastad, that says actually for linear equations there's a threshold at 1/2. It is NP hard to do anything better than 1/2, so above 1/2. Thanks, yeah, linear equations over GF2. If you're over GFP, the hardness would not be 1/2, it would be 1/p. And what is this 1/2? It's because over GF2 you can just select at random. Every variable will get one of two options, and half of the equations will be satisfied. And what Hastad is saying is that nothing can do better than this silly random assignment. So we will get to this this kind of theorem in the third lecture. As I hinted in the beginning of the talk, the unique gains conjecture predicts that such a behavior will happen for many approximation problems, much more than just linear equations. At this point, we know this theorem for several or many interesting problems, but there are many interesting problems that it's quite open. Okay, so for the next part of my talk, I basically want to discuss how to construct a PCP, or how this PCP verifier algorithm works. Okay, so let's look at 3-colorability. It will be my focus. It's enough to talk about 3-colorability, right? Because 3-colorability is NP complete. It will imply it for any other set. And just recall that what is the thing we are trying to construct? It's an algorithm that reads the input graph, has some randomness, and then it looks at only a few bits in the proof and accepts or rejects. So how will this, and of course, it has this completeness and soundness guarantees. how will this algorithm behave? So here is some graph. So in this graph, you should think of this vertex as being identified with this vertex, and the y is the same vertex. So is this graph three-colorable? And I need to verify it. Okay, so here is a coloring. This is supposed to be a proof that this graph is three-colorable. And there is an NP verification algorithm. You just go edge by edge and check. Okay, so I start. The proof here says that this is black and this is red, and on the other hand, you must put the same colors because it's the same vertices. And then you see that this is forced to be blue, and then this is forced to be black, and this is forced to be red, and this is forced to be blue. And if you walk from the other side, in the end, you see that there must be a contradiction. Okay, so this graph isn't three-colorable, but this is a very good proof to try to fool me into thinking that it's three-colorable, because there's only one problematic edge, right? All the other edges are good. And you can, of course, see that this strip can go on for a very long time, and only one edge will be violated. Okay, so if you were attempting to construct a PCP verifier to check colorability, three-colorability of this graph, well, I mean, a naive thing to do it would be to just check a random edge to expect a proof, a coloring of this graph, check a random edge, and you would be fooled, most likely, to thinking that the graph is three-colorable. Okay? And the problem is that it's almost three-colorable. There is a coloring that satisfies almost all the edges. And that's the difficulty here. Of course, it would be very nice if you only ran this naive algorithm on graphs that don't have these problematic colorings, don't have colorings that are almost. Okay, and this is going to lead us to this definition of what is a robust graph. Okay, so let's talk about robustness of a graph with respect to three-coloring. Start with some coloring, 1, 2, 3 of the vertices. Now, for this coloring, for every edge, you can compute whether this coloring violates this edge or not. Okay, so basically, we get a new function on the edges that is 0 for on every edge where the colors are different, the function gets 0, and on every edge that the colors are the same, it gets a 1. So it basically marks for us which edges are problematic. In fact, what we have here is an operator that takes a three-coloring into a function on the edges. Okay, so take all possible vertex colorings into a bunch of functions on the edges, and the operator is defined like we said. For every edge, you put a 1 only if the colors are problematic. Now, by definition, delta of f is 0 on all the edges if and only if f is a three-coloring. Okay, so if you're 0 everywhere, this is equivalent to being a perfect coloring. What ideally we would like is that even if you're almost 0, this can only happen if you're close to a three-coloring. So you want that whenever you're close to 0, it already means that you're close to 0 in the other sense. So one sense is if only few edges are violated, and the other sense is that you're close to an actual, honest three-coloring.
Close means what?
Close means what? So there's two notions of closeness here. If I look here at just functions on the edges, just count how many edges are 0. I don't know who was asking. How many edges are 0, or how many edges are 1, and normalize by the number of edges. So it's just a fraction of edges that are unhappy. Okay, so the two norms that we have here, one is the norm here that measures how many edges are being violated, and we always normalize. So this is a number between 0 and 1. And the other measure is how close f is to a color. Again, what fraction of vertices need to change color to make you a proper coloring. And in case in your graph there is no proper coloring, then just define this distance to be 1, the maximal distance normalized. Okay, so ideally we would like to have a comparison between how many edges are violated and how far we are from the good set. And that will be our definition. So let's say that this mapping delta is robust if this ratio, when you minimize over all possible colorings, but only those that are not proper colorings, otherwise you would have 0 divided by 0. So you go over all f's that are not proper colorings, and you compare the number of edges that are violated to how far you are from the good 0 set. Okay? If these two things are comparable, meaning there's a lower bound, a constant lower bound, then we say that this delta is robust. Okay, so this definition, the way it's written here, is intended to resemble some expansion. We'll talk about it soon. I just want to say that a graph is robust when the only way you can reach very few violated edges is because you came from a true coloring. Of course, if you started with a true coloring and you randomly flipped a few bits, you may violate some edges, right? So you can always start with a good thing and perturb it and ruin a few edges. And robust means that this is the only way to satisfy almost all the edges. Okay, and this definition, somehow it resembles definitions of expansion and Rayleigh quotients, which we will see tomorrow. So tomorrow we will talk about this definition in this slightly bigger context. Okay. So now I want to describe the PCP theorem as an algorithm that takes a graph G and embeds it in a new graph H, where H is robust. So it's some kind of robustification algorithm. Okay, so this is our approach. And this is what the PCP theorem says. It says that there is such an algorithm for moving from G to H, so that two things happen. First of all, G is 3-colorable if and only if H is 3-colorable, but also H is robust. Okay, so for H, there is no situation like in this Möbius strip that it's not 3-colorable or it's almost 3-colorable. No, H will be robust. If it's not 3-colorable, it's not 3-colorable. A lot of edges are going to be upset. Okay. Okay, so there are two known proofs for this theorem. The first proof, the original proof, uses low-degree polynomials which give special error-correcting codes. And I won't talk about them today. They will appear tomorrow, not a lot. And the second proof is this gap amplification, which uses expander graphs, which I will now describe. Okay. Okay, so in this proof, we want to start with G and construct this robust graph H, and we do it gradually. Each time we double the robustness. Now, the robustness is a parameter that is normalized. So if you double the robustness and it starts from something small, it will, after a bounded number of steps, reach a constant. Okay, so the value that we will keep track of is this delta, which is the smallest fraction of violated edges. Okay, so if you have a graph G, you look at all the colorings, and for every coloring, it violates some number of edges. Delta is the smallest such. Okay, so if the graph is 3-colorable, delta is 0. Okay. If the graph is not 3-colorable, then you must violate at least one edge, so delta is at least 1 over E. And what our proof will do is that at every step, if delta was 0, it will remain 0. If delta was non-zero, it will double. Of course, you can't double above 1, so there will be some threshold. After this argument won't work. So you double and double until you reach some constant. Okay, so let's look into the amplification step. How do you do this doubling thing? So this has two sub-steps. One is this gather step, where you double this delta value, but you do it not by staying with 3-coloring. You move to some other more generalized construction, which is like a sheaf. And in the second step, you return from this generalized situation to 3-coloring. Okay. Okay, so let's do this gather substep. So imagine that this is your graph G, or part of your graph, the things in black. And you have some coloring instance on it. And now you define a new graph H. So the graph H will have the same vertices as G and almost the same edges as G. So in H, you connect vertices U and V if they are at most T apart. So maybe this vertex will now be connected to this vertex. Okay, but you can even think of T as being 2. So the edges in H are connecting slightly further away vertices. What is interesting in H is that it's no longer a coloring problem. It is now a generalized coloring. So for every vertex, for example, for this vertex, you're not expecting anymore a coloring for this vertex, but rather you look at the neighborhood of this vertex, and you expect colors for all of the vertices in this neighborhood. Now, how big of a neighborhood? It depends on this parameter T. So in this picture, T is just T is 2, and this would be 1. So you look at all the neighbors at distance at most, I guess I'm missing an edge here, a distance at most 1 from your vertex, and you expect a local function that gives a coloring just to this part. Okay. Now you only allow local functions that are locally valid colorings. Okay, this is important, and also it's okay. There will always be local colorings, right? Because if locally you already find that there is some problem in doing a 3-coloring, then you know your instance is not 3-colorable. You can just output no and be finished. So locally you have 3 colorings for every vertex, and then what are your checks? So for every vertex you expect a local coloring, and for every edge in H, you now look at the 2. So if you have an edge connecting U and V and H, you look at the 2 local colorings, F sub U and F sub V, and you must check that they are consistent. Okay, so for example, you get a local coloring for this neighborhood. It tells you the colors of all of these vertices. Okay, and you also get a local coloring for this neighborhood. So you get, again, the colors of all of these vertices. Now this vertex appears in both, so it must get the same color. Okay, so this is what it means to be, for these local colorings to be consistent. So it's like a little sheaf over the graph G. Okay, and now again we define this operator delta. What is the delta now? It takes a bunch of local colorings and it gives values to the edges. Okay, so it tells us which edges are happy and which edges are not. So we will define delta at a point, at an edge UV, to be 0 if FU and FV are consistent, and to be 1 if FU and FV are inconsistent. So again, now you're not mapping from 3 colorings to edges, you're mapping from generalized colorings to edges. But it's the same idea. Delta just gives you an indicator of which edges are unhappy.
When you talk about consistency is for vertices, right? Why do you say edges?
Thanks.
One also checks if the edge is colored properly. Or?
Yeah, let me say it again. So U and V are still going to be vertices, but for U, you don't get a color. What you get is an entire local function.
I'm talking about the consistency between FU and FV. So they have to be consistent on the vertices.
On the vertices.
Right. So you wrote their edges because for
Where did I write?
For each edge UV in EA, check consistency of the local colorings FU, FV.
For each edge UV, you check the consistency between FU and FV.
But for each vertex U, or why are we
so I have here, I have my graph, I have U, I have V. U has many neighbors in here, and F sub U gives me a coloring of this entire neighborhood.
So by consistency you mean, okay.
Yeah, let me just finish so that it's not unclear. And then I have also for a V, I have some neighborhood, and I have F of V, right? And the consistency between FV and FU is just checking that everything in this intersection is consistent. And when I say everything, I mean the vertices. Yeah. Any more questions?
Yeah, the parameter t. How does it work?
Right, so t is like the radius of this ball. And for the analysis, you want t to be a bit big, like 100 or 1,000.
Independent of.
But it's some constant. Okay, it depends on the expansion of the graph and stuff like that.
What's to stop it getting? What's limiting it?
What's limiting it? So we will soon need to take this whole thing and encode it, and we want this to be constant size. So that it kind of causes some blow up in this construction. So we want it to be constant. Okay, so at this point, we just converted ourselves to some more difficult problem. But you see that because each u and each v kind of are aware of further away vertices, it might be that if there was some inconsistency here, it will propagate and it will affect more edges. Okay, and this is our goal. We're trying to propagate the bad edges. Okay. Okay. Anyway, it should be clear that if we started with a perfectly three-colorable graph, there is a way to continue this, and you will assign local pieces of this global coloring, and everything will be consistent. And in this new instance, you still have perfect consistency. The claim, and this is the interesting part, is that if the original graph was not perfectly colorable, there were some problems, maybe even one edge that was problematic, then in this new graph H, you will have more problems. So there won't be only one pair of U and V that are unhappy. There will be a bit more. It's this neighborhood that around them. And notice that this is normalized. So when we say delta with this tilde of H, the tilde just refers to the fact that it's not a three-coloring. It's this generalized thing. When we look at this delta, we normalize by the number of edges in H. So H had more edges. So when we say that this is double this is already after the normalization. So something really is getting doubled. Okay, and the reason this happens is because G is an expander graph. And an expander graph, no set of vertices has too many edges inside. There's always going to be many edges going outside. Right, so if you want, you can think of this H as some kind of sheaf, and then you're talking about the sections in this sheaf, and you say, okay, there is no global section, and in fact, there's more violations than there were before. I don't know if this is meaningful or not. Just to say what this, why this doubling happens. Okay, so I want to say that if delta of G was something, then delta of H is double. Okay, and for this, I need that G is an expander graph. Again, this is a graph where every set of vertices has many edges going out. So notice that now if you have a bad edge, all of the neighbors will notice it, right? Because even if you're a bit away of this edge, but you're neighboring, you know the values of this edge, so you will notice this problem. See, if you have a bad edge between some u prime and v prime, and u is a neighbor of u prime and v is a neighbor of v prime, oops, then because this radius is big enough, then u and v will notice this problematic edge. Okay, so if we assume, and this is a strong assumption, but let's assume it, that when you have a choice of local coloring for every vertex, they agree with something global, then you see that there is a problem. You think that there is some global coloring. Every vertex locally sees a part of it. And because this global coloring has some problem, then this vertex U cannot be consistent with this global coloring, because locally, what this vertex U is seeing must be a valid local assignment. So it cannot assign values here according to this global thing. It must deviate. And similarly, this guy must deviate. So a lot of vertices that are in the vicinity of this edge must deviate from anything global. Of course, it might be that there is nothing global and they all answer locally and they're not at all connected to anything global. So you need to believe me that that all these consistency checks are forcing them to be global. And this is, in fact, only true if the underlying graph is an expander. You can see that if this part is perfectly colorable and this part is perfectly colorable, then somehow the problem won't propagate. There will be only a tiny bit of propagation along this path. So you really need that the graph is an expander for this whole argument to work. Now, let me address this issue of global of agreement with some global function. I think this is an important part. It occurs in other proofs of various PCP theorems. We will see it again tomorrow and on Tuesday. And this is an issue of relating local agreement to global agreement. So I guess I have a cartoon. I think this question is very interesting and kind of very important. So you have some space. It's not a sphere like it looks here. It's some maybe complicated space. And you cover it by a bunch of small pieces, and they are overlapping. And then you try to have local functions for each piece. Like in our case, these are local 3 colorings. And you want these local colorings they try to agree with each other. They're doing their best to agree with their neighbors. Okay, and the question is, suppose they have a lot of agreement pairwise, 90%, 99%. Does it mean that there is a global function on the entire space that agrees with many of them? Okay, and this is not always the case, and it's very interesting to find non-trivial spaces where this behavior occurs. Okay, and in this proof, it doesn't really occur in the strongest form. It occurs in some meaningful way. But we now know of much better spaces where this is even much stronger. And we will talk about this tomorrow and also on Tuesday. On Wednesday. Yes, I'm still on Israeli weeks where the first day is Sunday. Anyway, okay. So, so to wrap it up, we don't have a lot of time left.
You didn't say what happens if G is not an expander.
It doesn't work. So, no, you're right. What I forgot to say, I mean, you started with, thanks for reminding me this, actually. Oh, this is terrible. Let me do this. Okay, I'm not using this. Just to say, I started with a graph G. I wanted to know if it's 3 colorable or not, and I need to convert it to a graph H. It's not an expander. There's nothing to do with expansion on G. But then I showed you some construction that works if G is an expander. So Peter is asking, but what if G wasn't an expander? So really, you don't need to worry about that, because if G was not an expander, you can just overlay on G edges of an expander. Okay, and then when you define this sheaf, these local neighborhoods, you take into account the edges from this overlay. But you don't care about the coloring of those edges. For those extra expander edges, you allow them to be colored anyway, because we don't care about them as coloring edges. All we care about is using this expander as a kind of geometry to allow us to propagate the coloring. So, okay, I mean, it's a slightly, it sounds subtle. It's not very deep. You just use this.
But you were saying that this thing is actually used not just in hardness proof. So in that case, you would have to overlay explicit.
With a specific explicit expander, of course. Yes. Okay, so now we'll take 5 minutes to scroll back. Okay, more. Okay, so I said that there's 2 substeps. I so far showed you just the gather substep where we collect more information, and this increases the gap. We need to then return to 3 coloring. I'm not going to have time to talk about this. Basically, you do some kind of local replacement where every kind of subset in your generalized coloring is now replaced by a whole bunch of vertices, and you encode them by some coloring problem. Basically, what's happening here is that there is a local replacement with a gadget. And this is highly non-trivial. You basically need to use an entire PCP theorem, but a much weaker one. So these we know how to construct quite easily, and I won't have time to talk about it now. In fact, on Wednesday, we will see this kind of local replacement again, so maybe it will make more sense then. Anyway, to wrap up the proof, so this is responding very slowly. Sorry. We have one step that increases the amount of violations, but at the cost of not being 3 coloring anymore. Then we have a step that regains this 3-coloring form. And the point is that every pair of such steps spreads the violations a bit further. And after you finished all the steps, all the vertices kind of get a feel of these violations. Yes. So to summarize, we have this sequence of embeddings from G to G1, G2, G3, all the way up to H. Every step maintains the 3-colorability. If you started with a 3-colorable graph, you will end up with a 3-colorable graph. But if you started with something that was not 3-colorable, then the number of violations will double, which is very good. And in fact, you only need to double logarithmically many steps. So you get a polynomial time algorithm that transforms G to a new graph H that also has this robustness. So I'm sorry for I'm a bit behind schedule. Mm-hmm.
So at each step you multiply the size of the graph by something?
By some constant, yeah. And so if there's logarithmically many steps, it's still polynomial. Okay. So each step was kind of local, but because every step you gather some information on an expander, in the end, every vertex kind of gets affected by the entire graph. And if there was a violation, it has been properly spread around. Okay, there is some remarks here about the construction. It's polynomial, but really what we would like is much more efficient, like G log G or even linear in G. And for this kind of iterative elementary steps seems not well suited for that, and you need something better. So that's one thing. Another thing is that the H that you get in the end, it's hard to know what it looks like. It has been constructed by a bunch of iterations. And so if you give me one vertex of H and you tell me who are the neighbors, it's very hard for me to describe. It would be nice to get an H that is kind of beautiful and looks like a Cayley graph or something that you can see what it looks like. Okay, so maybe I just go like this, much better. Okay, so here's what we talked about today. I described the PCP theorem. Every NP set has a PCP verifier that enables probabilistic local checking. I described how it's equivalent to hardness of approximation, and then we defined this notion of robustness of a graph, and we showed some kind of algorithm that slowly robustifies a graph. And this relies on expansion. And let me just finish by saying my plan for tomorrow and the next day. So tomorrow we will talk about high-dimensional expanders. This robustness that we define, we will put it in the same ground as some generalized definition of expansion, and we will describe some local to global theorems on high-dimensional expanders that are very similar to the kind of theorem that the PCP is. And then we will talk about these beautiful objects and just look at some combinatorial properties that they have that are already good enough for local to global, and maybe they can be useful for other constructions. And then on Wednesday, we will talk about this very hot topic of unique games, try to see how the landscape is very beautiful for approximation if it's true, and try to see whether or not it's true. There are some different kind of expanders that these unique games constructions might live on, like the finite field Grassmannian, and we'll see about that. Okay.